Good morning. A couple of announcements. Homework deadlines have been shifted, so there's now extended a little bit because we are working through node voltage analysis. Original deadline was on the 6th. It is now later in this week. And so I'll go over the techniques of node voltage analysis and cover a couple of problems from the homework and then answer student questions. And that way students have a couple more days to get the homework done. Okay. Quiz one, which was a resubmission of the earlier one, the deadline is tonight. So please make sure you upload it in time and also do the question mapping, the answer mapping to the questions. And then hopefully you've already done that for quiz two, right? That was the deadline was already passed. So again, if something is amiss, I'll email students and let you know. Okay. All right. So let's get to node voltage analysis. Leave. These were the slides we're talking about in this was what I had covered, I think last Friday. So we were discussing the concepts of a node, a branch, a loop, and a mesh, right? So nodes and mesh, they are the two characteristics that we will use for node voltage analysis and mesh current analysis. Identifying meshes is rather straightforward. Nodes sometimes can be tricky, but as long as you keep that fundamental principle in mind, if there's only a wire connecting two or more nodes, then they're all the exact same nodes. Okay. So we had the circuit, straightforward circuit. We had one source, 4 resistors, and we have 4 nodes in there. So identifying the nodes is rather straightforward in this circuit. One of the things I pointed out was before we begin any kind of analysis on the circuit, it is possible to reduce R3 and R4 into one single resistance. And thereby we can eliminate one node, right? The next thing I want to talk about is branch currents. So any component that connects two nodes is a branch. Okay. Now the branch of a circuit could be a series, could be a parallel, could be any other connection also. So technically I can say the resistor between C and D is one single branch, and between D and A, which is R4, is a different branch. But because they're in series, they share the same current. So if they share the same current, I could also say that R3 and R4 is the exact same branch. No difference, right? Because the same current flows through both resistors. Now, once you have branches and we have currents flowing through there, the current that flows through every single branch is defined as a branch current. This is going to be important when we apply node voltage analysis. This is the absolute first step that students need to take. You identify the nodes, you label them, and then you assign branch currents to each and every single branch. Without assigning branch currents, we cannot apply KCL. All too often, I've seen this over and over and over again. For so many years that I've been teaching these techniques, students will skip that first and the most important step. Okay. So think of this as the foundation for your analysis. If the foundation is not correct and set up correctly, then the rest of your solution is likely to be error prone. Okay. So branch currents are the currents flowing through a branch. Let me write that down here. I'm going to use red ink for this so that you know from the you can distinguish the annotations. Let me write down actual current. Okay, branch currents. For the purposes of simplicity, if I was to look at this circuit, I would simply call them IR1, IR2, IR3, and IR4. Automatically notes that IR1 is the current flowing through R1, and so on and so forth. Okay. Now let's go to the actual technique. So the technique is based on KCL. We generate equations by applying KCL. Okay. At the beginning of our analysis, when we assign branch currents, we don't know which direction they are flowing. So we make assumptions. But those assumptions are based on certain logic. If I know that the source is connected like this, which direction is the current flowing for that source? Bottom to top? Is it going up or is it flowing down? Is it going up? Anyone else? No one else? For a source, current always goes from minus to plus. Again, this is a law of conservation of energy. Current is like any other physical quantity, always goes from plus to minus, except when it's a source. For a source, it flows from minus to plus. Otherwise, our equations would never balance out. Okay. So current through resistors to any other components will always go from plus to minus, except when it's a source. For a source, it always goes from minus to plus. There is only one source in this circuit, so our assumption is made a little bit easier, because if the current is flowing up, it has nowhere else to go except from left to right. And when current goes from left to right, still staying with the same passive reference configuration, current always goes from plus to minus, meaning if it's entering a resistor from one end, the point of entry is plus, point of exit is minus, causes a voltage drop. Okay, so this assumption is made by you. Okay, identifying the branches and labeling the branch current and the direction is made by you. As an engineer, it is part of your analysis. And this must happen at the very top. You're setting up your solution. Does that make sense to everyone? Okay. So we assume the direction. In this example, the direction is already given to us. If it's going from left to right, then positive is on the left, negative is on the right. Yes. That is correct. So the question being asked is the polarity of the voltages, is that assumed by us, meaning whoever's trying to solve the problem? The answer is yes. Because at the beginning of the problem, nothing is given to us except the values of the components. So we begin by assigning branch currents, and from the branch currents, once we assume the direction of the branch currents, we can now assume the polarity. Logically, it dictates that if the current is entering the resistor from the left, then it must be a higher potential. So it's plus on the left. Make sense, everyone? Okay, so now let's label the nodes A and B. So we have A, we have B. If we apply Ohm's law, we can express the current I as the voltage VR divided by the resistor R. In this case, I is unknown and VR are also unknowns. So those two are unknowns. The only known value is the resistor R. Okay, that's the only known value. So again, That's after applying Ohm's law. Okay. And I would also strongly recommend students do not skip this step. In the books or in some of the notes, you might see that the author or the solution directly writes this. I would strongly advise against doing that. This is when errors happen. Even after emphasizing this, come quiz time and exam time, I still see solutions where students have this as the first step. And then there are invariably errors in the solution. The reason this is important is because once you have VR over R, now we can describe VR as the difference between A and B. And this is where the assumption is important. If we assume that the current is flowing from left to right, that means we are assuming VA is higher than VB. So in our equation, it becomes VA minus VB. Okay, we are describing the resistor voltage VR as the difference between the two endpoints. And the two endpoints are VA and VB. And because we assume the current as flowing from left to right, it is VA minus VB. If another student chooses current flowing from right to left, then their equation would be VB minus VA. But the answers will still be the same. Because when we apply KCL for one node and we apply KCL at another node, all comes out to be the same thing. So let's take a pause. You think over that. Let me know if you have any questions. Yes. So a question being asked is, in a quiz or an exam, should we show the notations? The answer is yes. So it's not just a matter of earning points. This is the actual steps that students need to take. And again, sometimes you might want to skip steps. Penalty deduction might be minimal, but if you make an error, then there's no way for me to actually even assign any points. Okay. So in my questions, I typically always state, assign branch currents, label them, and I give like 1 or 2 points for those. And so it will state right there in the question itself. Okay, so that's how we are generating the equation for the current I. Now, how do you generate more equations? Well, you're going to apply KCL at node B. We can apply KCL at any number of nodes in a circuit. Depends on how many equations we need, right? So if you apply KCL at B, this again determines the direction of the current, determines what equation I generate, right? So here the directions are already given to us. I1, I2, I3 are already labeled. So the KCL is going to be I1 equals I2 plus I3. All currents entering must equal the sum of currents leaving that node. And so here's the thing. If different students choose different directions for their currents, there are 3 currents in there, so, right? So there's 8 different combinations. 8 different combinations of the currents flowing in there. So 8 different students could choose any one of those combinations, yet their final answer will all be the same. It will not change. Because if a student chooses, let's say, exactly as how I have shown here, they would have VA minus VB over R1 is equal to VB minus VC over R2 is equal plus VB minus VD over R3. Now, if somebody chooses a different direction for, let's say, I3, so instead of having this term, it would actually be minus VD minus VB over R3. the KCL equation would change, and the node voltages would also change, because I'm assuming the current's flowing in the opposite direction. But the equation, the final answer, the final equation would not change. So this is if I3 direction was opposite to what is shown, meaning it's going from right to left. Okay, let's take a pause and then let me know if you have any questions. Did that make sense? Yes. So the question being asked is, in under what circumstances would we assume that the current I3 is flowing in the opposite direction? One of the answers, or one of the possibilities, if there is another source on the right. It could also be that we simply just want to make an assumption that way. So that brings up a good point. So if you wish to practice your skills, you take the same circuit, you change the directions of the currents. And again, as I said, at this node, you have 3 currents. Each current has 2 possible directions. So you have 2 raised to n combinations. 3 currents, meaning you have 8 possible combinations. You can write out, once you solve it with one possible combination, just flip the currents one at a time. I mean, just try out another 3 or 4 combinations. Generate your equations and see if you can end up with the same answer. That's good practice. Okay. Because you already know the solution, it already works, everything's already there. Okay. All right. So summing up node voltage analysis, first thing is you identify all the nodes and select a reference node. This symbol, 3 horizontal lines in the shape of a triangle, refers to ground or common terminal. Sometimes ground is also referred to as G and D by its acronym. More importantly, it also refers to the reference point in a circuit. More often than not, it is the negative end of the voltage source. Okay, so in the homework problems and many of the circuits, you will see this symbol connected to the bottom of the circuit. And so that's the node we take as the reference node. But the important thing to understand, it doesn't matter what that reference node is. You can pick and choose whichever node you want. And I'm going to show that with the homework problem. Okay. So first step is to identify all the nodes. You reduce the circuit down to as little number of nodes as possible. And then you choose a reference node. Ideally, choose negative end of the voltage source. There is a very simple reason for that. It's because a voltage source will maintain its voltage at either end of the terminal. So if you choose the negative end of the voltage source as your reference, you automatically have an answer for the voltage at the other node. So you automatically eliminated 2 nodes. Okay. Then next is to assign branch currents to all branches, assume current direction, write the KCL equation, each node, generate your expressions. Apply Ohm's law and express each branch current in terms of the node voltages at either end of the resistors. If you proceed in this step-by-step manner, you can solve any circuit you want. Okay, doesn't matter what kind of circuit it is. We just apply these steps as they're outlined. Okay, and then you generate your equations. And once you generate your equations, you'll have a set of linear equations in the form of ax plus by plus cz is equal to d. X, y, and z are your branch currents, the unknown variables, and then you solve those values. All right, any questions before we get to the example? No questions? How many of you have submitted the homework? Okay. Do you have any questions about that? Yes, no? You're all done? Yes, go ahead. 2 point. Let's see. You said this one, 2.49? Oh yeah, this one's how many equations? So question being asked is about 2.49. How many equations, for those of you who completed and submitted this, how many equations did you have? 3, 2, 1. This one's rather straightforward. So what if I tell you can solve this with only one equation? So let's go to our notebook. Let me post this here or paste this here. Okay. All right. Okay. So first step is to identify all the nodes in the circuit. How many nodes do we see? So I can write down this 1, this 2, this 3, 4, 5, multiple connections everywhere. But between those connections, we have wires. So I have a wire going here to here. So that means this is one node. Same thing with here. So all of this is one single node at the bottom. Okay. And so I'm going to call this as node 3. All of this is one node. And all of this is also one single node. So this is node 1. This is node 2 and node 3. Okay, so there's only 3 nodes in the circuit. There are 2 sources, 3 nodes. The reference node is already shown to us. Okay, the reference node is already shown to us. So V3 is already shown. However, what I'm going to do is I'm going to choose node 2 as my reference. So therefore, what is the value for V2 for the purposes of this analysis? 0 volts. Absolutely. And hence, V1 is 10 volts. So out of 3, I have the answers for 2 of the node voltages. Only unknown left is V3, one node, one unknown variable, one equation. And that's it. Only one equation is required. Okay. So now, yes. So question being asked is, why is V1 10 volts? The answer is that the voltage source has a property, meaning it will supply its rated voltage between its two terminals, no matter what is connected. So if we choose V2 as our reference, then V1 is 10 volts. If we choose 1 or V1 as a reference, then V1 would be 0 and V2 would be minus 10. So let me note that here. And as practice, I think I would recommend that students solve this problem by taking node 1 as the reference. So if 1 is the reference, then V1 is 0 volts and V2 is minus 10 volts. Okay, minus 10. And you'll still be left with one unknown. If 3 is a reference, then V3 is 0 volts. And V1 and V2 are both unknowns. So we need two equations. However, we can also write because it's a voltage supply and V1 is at the positive terminal, I can write V1, let's say Vs, supply voltage, V1 minus V2 is equal to 10. So the voltage of the voltage source can be written as V1 minus V2 equals 10. And this is true for any voltage source. If you have a voltage source, positive terminal is always higher than negative terminal. You can write an equation saying that supply voltage Vs is equal to its positive terminal minus negative. So the value, if it's a 20 volt supply, V1 minus V2 is 20. And that's an additional equation that we have. So this combined with the two equations we generate here, we would be able to solve that problem. Okay. So next thing to do is to assume branch currents. See, IS is already given to us. So I'm going to leave that as it is, not going to do anything with it. Okay. Now let's assume the direction for the other currents. So I have IS going in this direction, but note, it is going from plus to minus. For a source, current always goes from minus to plus, right? Our analysis or our steps do not change. Just because it's shown as going in the opposite direction, our analysis does not change. We still follow the exact same steps. We ignore everything else, follow the steps. All right, let's choose a direction for R1 and R2. All right, so let's say the top current, I choose going this direction. Let me call it IA. Then I have IB. I'm going to choose here going down. And let's see, R2. Let me choose going down. Here, I can try and apply logic, but there's no clear indication which direction the current will flow. So I'm just making just an assumption. Okay. The logic does not lean one way or the other. So I'm just assuming it going down. That's all. Now that I have all three branch currents, I'm going to apply KCL. When I apply KCL, and this is assuming three is my reference point. If I apply KCL, I have three currents. So I have IB plus IC are entering node 3, and the 1 amp current source is leaving. So IB plus IC is equal to 1. That's my KCL. IB, because it's coming down, I can write as V1 minus V3, or let me say VR1 or R1 plus VR2 or R2 is equal to 1. Again, first I have my KCL, then I have Ohm's law, and now I express it in terms of the resistor voltages. VR1 is going to be V1 minus V3 or R1, and VR2 is V2 minus V3 or R2. So what do I have? I know values for R1, I know value for R2. For the purposes of this analysis, sorry, this is not 3 as reference, this is 2 as reference. Sorry, 2 is reference. Okay. So if 2 is my reference, in this equation, V2 is 0, V1 is 10. V3 is the only unknown left. That's it. So I'm going to solve this, and I can write 10 minus 0 over R1. What is the value for R1? At my end, R1 is 3 ohms and R2 is 12. R1 is 3. And R2 is 12. That's it. One unknown variable, one equation. If I solve this, I will find the value for V3. So I have multiply everything by 12. I get 40 minus 4 V3 minus V3 is equal to 12. And then I have 5 V3 is equal to 40 minus 12. So V3 is 28 or 5. Somebody check my work, please. Or all of you check my work. Let me know if something doesn't make sense or if something is incorrect. What do you all have? Same? Now, important concept following this. What to do if I choose a different reference node, right? I'll just wait for a few more seconds. unless I made an error in my calculation somewhere. Let me see. So VR1 is V1 minus V3 over R1. We've got V2 minus V3 over R2 equals 1. 10 minus V3 over 3. 0 minus V3 over 12. Multiply everything by 12. Gives me 4 times 10, 40. 4 times V3 is V3 minus V3 plus 12. 5 V3 is 40 minus 12. 28 over 5. Okay. So now I have the values for all 3 points. So this is what we need to do at the end. All right. First, start with the reference node. I'm going to draw a one-dimensional chart. Okay, just 1D. And 1D chart is this is a one-dimensional chart or a graph that illustrates the level of the voltages. So I have A, B, and sorry, a node 1, 2, and 3, right? For the purposes of this analysis, I chose node 2 as my reference point. So node 2 is at 0. So I'm going to write, or I'm just going to draw a horizontal line. This is node 2. Node 2 is my reference point at 0 volts. What is the value of node 1? 10 volts. That means node 1 is 10 volts above node 2. This is not going to change because there is a voltage source between the two. This difference does not change. Okay? This difference does not change. That is the most important point you have to remember because of the voltage source. The difference or the distance between those 2 points is going to remain at 10 volts. That does not change. Now, node 3 that we found, 5.6, is that above node 2 or is it below node 2? It's above. It's 5.6 volts above. So let's just say it's somewhere here approximately. So it's 5.6 volts. Now that you have this one-dimensional chart and you can see the distance between the 3, here's the important concept. Once you have a circuit and it's energized and voltages and currents appear in that circuit, as long as nothing else changes, meaning as long as the voltage and the current source, nothing changes, the distance between any 2 points, electrically speaking, is going to remain fixed. It's not going to change. So between 1 and 2, the distance is 10 volts. It remains 10 volts. Between 3 and 2, the distance is 5.6 volts. It is going to remain 5.6 volts. It doesn't matter what you choose as your reference point. So now seeing this graph, what is the distance between 2 and 3? 5.6. So now if 3 is my reference, as it's asked in that problem, if 3 is my reference, what is V3? Then what is V2? Exactly, minus 5.6 volts. That's it. So again, this is an important concept. Fundamental, basic, but very important. The distance between any 2 points, the electrical distance between any 2 points, the difference will remain the same. It's not going to change. A reference point can change. A reference point is just our baseline. did I talk about the height analogy in your class, right? Our height is the same. It doesn't matter what my reference baseline is. The distance from the end of my toes to the top of my head is going to remain 5.6. It's not going to change. If I change my reference point, the base, top of my head, I can say is at a different level. But the distance between the 2 points does not change. So if V3 is my reference, V2 is minus 5.6, what is V1? .4 volts. You'll have to speak up. My ears are not that good anymore. Lots of listening to loud music in my youth with headphones plugged in. So 4.4 volts. So if I enter the answers in there, let's see if they turn out to be correct or incorrect. All right, so what did we say? V1 was 4.4 units. 4 volts, correct. And this should be 5, no, this should be what? Minus 5.6. And correct. Okay. And the final question is to find the value for IS. But before I go to that, any other questions regarding the process? Did the process make sense? So you could choose any reference node and still do the same thing. You can choose 3 as the reference and work through the solution. Choose 1 as a reference and go through the solution. Yes. So the question being asked is, why did I choose node 2 as my reference? Simply because it's connected to the negative end of the voltage source. So that eliminates 2 nodes right off the bat. If I choose the negative end of the voltage source as my reference, the value for the reference is always 0. I'll automatically have an answer for the voltage at the other node. There's no right or wrong. You can choose 3 as the reference as shown in the as shown in there. Then you'd have this extra equation anyway. V1 minus V2 is equal to 10. That's always there because that's the voltage source. Yes. This one. Oh, question being asked is about this term is because I assumed my direction for IC as going from top to bottom. That's simply an assumption. The directions are simply an assumption on my part. I could very well solve this by choosing current IC going up in the upwards direction, and I would still obtain the same answer. So the directions for IA, IB, and IC are assumed by me. Okay, and because I choose IC as coming from the top to bottom, I'm automatically stating that node 2 is at a higher potential than node 3. Even though at the end, the answer says it's the other way around. It doesn't matter. For the purposes of this analysis, I'm choosing node 2 to be higher than node 3. And you saw at the end, my answers are still correct. I obtained minus 5.6. So it doesn't really matter. Yes. Because IB is going down. So it's V1 minus V3. All right, let's see. Let me, so about 5 minutes left. So let me get through IS. So IS, once we have the node voltages, we can calculate all the other resistor voltages in there, right? So IB is VR1 or R1. IC is this term right there. And IB is this term. So if I apply KCL at either end, I can apply KCL at, write it down. Let me just scroll down. Node 1 or 2 for IS. So I can write all 3 currents. If I choose node 1, I only have 3 currents. If I choose node 2, there are 4 currents. Doesn't really make any difference. You apply in both 1 or 2, doesn't really make a difference. If I apply at 1, at node 1, I have all 3 currents leaving. Nothing is coming in. So nothing is coming in. So it's 0. I have IA plus IB plus IS. IA and IB can be determined from here, right? Actually, okay, I don't have IA, but I have V1 and V2. So I need to find IA first. So this is going to be V1 minus V2 over R1. Once you have the node voltages, you can determine anything else in the circuit, right? You have V1, V2, and V3. So you can find the voltages across all the resistors. Once you have the voltages across the resistors, you can find the current that is flowing through each and every resistor. So IA, from my assumption, is going from left to right. That means I'm stating V1 is higher than V2, which is of course the case anyway. And so it would be V1 minus V2 over R1. The other way to look at it is R1 is in parallel with the 10 volt source. That means it is simply 10 divided by R1. Okay. So this is simply 10 divided by 3. And that gives me IA. And then IB, I can calculate from here. And you plug it in and you find your IS. Okay. And that's it. That's the solution to the problem. That makes sense? Once we have, again, as I'm saying, in mesh current analysis, our goal is to find the values for the mesh currents. That will come later. Node voltage analysis, our goal is to find all the node voltages. Once we have all the node voltages, we can calculate any other quantity in the circuit. You have the node voltages, we can calculate the voltage across every single resistor. Once you have those voltages, then we can find any of the currents through those resistors. Okay. Any other questions? We have a couple of minutes left. Actually, less than a minute left. Yes. Oh, I'll change those. Yeah, thanks. Thanks for reminding me. Okay, we'll end class here today and we'll pick up here on Friday. We'll just talk a little bit about supernodes and then we'll get into the mesh current analysis technique. Quiz on Monday. Again, every quiz has been posted since the beginning of the quarter. The quiz schedule, Monday is node voltage analysis technique. So practice as much as you can and bring your questions to class on Friday. All right, I'll see you all Friday.